So the idea of exact equation is great and all, right? Being able to have this function, then it gives you solutions right away, that's fantastic. But how do we actually solve them, right? When you're given an equation like this, you are just given m of x, y plus n of x, y, dy and dx equals 0. You're not told the function psi or that it even exists in the first place. So how do we go about determining if it's exact in the first place? And then once we know that, how do we actually find this function psi that makes this work? So for the first part, we have a trick from Calc 3. We'll look at the following. We know that this function m is the partial derivative of this psi with respect to x, and n is the partial derivative of this function with respect to y. So in that case, what do I know about the function m sub y, which is the partial derivative of m with respect to y? Well, that's just going to be psi of x, y. Second partial derivative is how they work. And similarly, partial derivative of n with respect to x is going to be psi sub yx. And what do we know about these two functions? Well, they're the two different mixed partials of psi, so as long as everything's continuous, they must be equal. It's giving you flashbacks to conservative vector fields in Calc 3. That is not surprising. These are very related concepts here. So the idea is basically then that the book states as a theorem, if m sub y equals n sub x on some rectangle, that's just a condition to make sure things work out nicely, then the equation is exact, and such a function capital psi exists. So if we determine that the partial m with respect to y equals that of n with respect to x, then I know the equation is exact, and there's a point to try to hunt for this function capital psi, because it's going to exist because the equation is exact. Now, how do we find this psi? How do we solve these equations? The idea is basically direct integration up to some adjustments with how this stuff works. So we have our equation here. Let's first check if it's exact. So we have that the function m of xy is 2xy, and the function n of xy is x squared plus 4y cubed. Check for exactness, I want to look at the derivative of m with respect to y, which is 2x, and the derivative of n with respect to x, which is also 2x. So because these two match, this equation is exact. So let's go about solving it. How do I solve this? I want to find the function psi of x, y, and I'm given two facts, because I know what m and n have to be. So I know that the derivative of this function with respect to x is 2xy, and its derivative with respect to y is x squared plus 4y cubed. Let's start with the x derivative here. So if d psi dx equals 2xy, then I want to just integrate. Since I'm now assuming that I just have x and y as two variables, I'm not really worried about the dependence of y on x anymore. I just have a function of two variables here that I want to use to solve this equation. So I just integrate this expression to give me then that psi must be integrating 2xy in x, 2xy dx is going to be x squared y, and then plus a constant. But now what's the constant here? This needs to be a constant with respect to x. Since I have y variables flowing around, this can actually be any function of y. Because if I take this expression here and differentiate it in x, this entire function vanishes because it does not depend on x, it only depends on y. That's the key point here. When I do this concept of integration, for the first one, if I'm doing x here, it's going to be a function of y. If I had to do the y first, this will be any function of x in this spot here. But now I can try to use my second fact. So this used the first fact here. Now I'll use the second fact. So I'm going to differentiate this here in y. So then d psi dy, based on my expression here, is going to be x squared plus a prime of y. But based on my information up here, this is supposed to be x squared plus 4y cubed. Now I can match both sides and then get that my function a prime of y must equal 4y cubed. That I can integrate to give me just y to the fourth. And then I can put that back into where I had my entire function psi in the first place to give me that as an end result, my function psi of x and y should be x squared y plus y to the fourth. And now I don't need to include a constant here. I can put it here in pink. Because the way I'm going to use this function is by then saying, therefore, the general solution is psi of x, y equals a constant. So really, I can kind of absorb this c into here, and it's not going to make a difference. Or x squared y plus y to the fourth equals a constant. If we had an initial condition, we could then plug it in to see what c had to be. But this is what we get for a general solution for this type of a problem. So the idea is basically, step one, make sure it's actually exact. And then use the fact that you know things about the two partial derivatives of this function capital psi, integrate in one variable, and then differentiate in the other, and match up terms to make sure it works. There's a second sanity check here, where if your equation wasn't exact in the first place, you would get to an expression down here where this a prime of y was not only a function of y. If you saw any x's over here, you'd be in trouble and realize it wasn't exact in the first place, and you had to, this isn't the way to solve this problem. But then once you integrate an x to get here, take this expression with an unknown function in it now, differentiate that in y to get down to here, plug that back in, and that leads you to the general solution for these exact equations. Gives you a way to find this function psi, and then use that psi of xy equals a constant to find the general solution to these sorts of problems.